Hi students, welcome to Swamy Sir's YT channel. So yesterday we discussed about the properties of charges. So today we are going to discuss one more topic in the electrostatics chapter. So that is Coulomb's law. Coulomb's law we are going to discuss. So now Coulomb's law is nothing but if two charges Q1 and Q2 are separated by the r distance, okay, r distance, smaller distance, then the electrostatic force between these two charges is directly proportional to the product of that charges and inversely proportional to the square of distance between them, so from these two we can write it as F is directly proportional to the q1 q2 by r square. F is directly proportional to q1 q2 by r square. Now proportional constant is 1 by 4 pi epsilon naught. So now here why I am taking epsilon naught means here I am keeping these two charges in the air. I am keeping in the air or vacuum. So if we keep the two charges in air which are separated by the r distance, then the force of attraction, force of electrostatic force between these two charges is F equal to 1 by 4 pi epsilon naught q1 q2 by r square. So now electrostatic force in the air between the two charges equal to the place of 1 by 4 pi epsilon naught. I am writing the small k. This is the electrostatic constant, small. For our convenience I am taking this one. So k into q1 q2 by r square. This is the formula. Now at the place of k is equal to the 1 by 4 pi epsilon naught. That value is 1 by 4 pi epsilon value is 9 into 10 power 9 Newton meter square per Coulomb square. Remember the numerical value and unit also very important, and this value we will use in the problems. Okay, next epsilon naught is the permittivity of the medium. That value is 8.85 into 10 power minus 12 Coulomb square per Newton per meter square. Here this epsilon naught is the permittivity of the free space or air or vacuum. Here we are keeping the charges in the air, so permittivity of that air. Next case what we are doing means we are keeping the similar charges by separating the same distance. So here in the air the distance between the two charges are only now, so same distance, and we are arranging this one in a medium. Then electrostatic force between the charges in the medium is 1 by 4 pi epsilon. Epsilon is the permittivity of the medium. Here epsilon naught is the permittivity of the free space. Here epsilon is the permittivity of the medium into q1 q2 by r square. We have the one more formula, that is nothing but relative permittivity equal to the, so permittivity of the medium to the permittivity of air. Okay na? So equal to, this is nothing but the k is nothing but here dielectric constant. Okay, dielectric constant is equal to the ratio of permittivity of the medium to the permittivity of the air. Okay, so the force, electrostatic force between the charges in the medium equal to the 1 by 4 pi epsilon place epsilon equal to epsilon naught, send this side epsilon naught k to q1 q2 by r square. This k is the capital K dielectric constant. This is our convenient. I am taking one small k value. This is the electrostatic constant. This one is the different. It's two are different. Now see here I have the force of electrostatic force between the charges in a medium equal to 1 by 4 pi epsilon naught k into q1 q2 by r square we are getting. But whenever these two charges are placed in the air, then the force of attraction for electrostatic force between them is F air equal to 1 by 4 pi epsilon q1 q2 by r square. At the place of 1 by 4 pi epsilon naught q1 q2 by r square, the place of this I am writing the from here F air. So now the force, electrostatic force between the charges in the medium equal to the electrostatic force between the charges in the air by k is the dielectric constant. Okay, from this we can write it as k equal to dielectric constant equal to the F air by F medium. That means one more definition for the dielectric constant is ratio of the force between two charges placed in air or vacuum to the force between the same two charges placed at the same distance in the medium. Okay, so this one formula, remember these formulas. And next we are going to write the Coulomb's law in the vector form. So whenever we are writing the vector form, so here we have the charge q1 and here the charge is q2. Okay, so whenever we are writing the Coulomb's law in vector form, we have to consider the sign of the charges also. Suppose if this charge is plus, this is the plus, both are the like charges, then repulsion takes place. Okay, repulsion. And next if this is the negative and this one also negative, same repulsion take place. between the like charges repulsion takes place. Unlike, suppose this is the plus and this one is a minus, then attraction takes place. Attraction takes place. Okay, suppose here I am considering I am taking the like charges. Like charges means these two are either positive or either negative. So now first I am going to find force on the first charge, q1 charge, due to the q2. Both are say like charge is no repulsion take place. That means force is acting in this direction. This will repel and it will move in this direction. Force is in this direction. So force on 1 due to the 2. Okay, F12 equal to the first write down formula. Force F12 equal to 1 by 4 pi epsilon naught product of these two charges q1 q2 by distance between these two. So from second charge to the first charge, the distance is r21. 2 to 1, r21. So here square of distance between them, r21 whole square into, so this is nothing but the magnitude. So to write the vector form, we need the magnitude as well as the direction. In this direction, in the force direction, we are assuming the unit vector, that is also nothing but the r21 cap I am keeping. This is indicating the unit vector in the direction of this force from the 2 to 1. Okay, now r2 cap I written. So now already we know vector has the magnitude and direction. Direction is represented by the unit vector here. So from this unit vector equal to the r21 bar by magnitude of this one. So this value substitute here. Then f12 equal to, we are getting 1 by 4 pi epsilon naught q1 q2 by r21 whole square. R21 is nothing but the distance between these two, magnitude only I am taking. So this is the vector by magnitude. Now see, now f12 equal to the 1 by 4 pi epsilon naught q1 q2 by r21 whole square, r21 cube into r21 bar. So this is the vector form of the Coulomb law. Okay, so f12 equal to 1 by 4 pi epsilon naught q1 q2 by r21 cube into r21. So if they ask vector form, use this formula. If they just if you want to find the magnitude, then if it is in the free space, then use this one. If it is in the medium, use this formula. If they are asking the vector form, use this formula. Okay, so now we found here force on the first particle due to the second particle, so we found this formula. Similarly, force on the second particle due to the first particle. So like charges we consider now, so repulsion. So this is nothing but the F21 bar. Okay, same way we will get this formula. Okay, now the force on second charge due to the first one is in this direction. Force on the q1 due to q2 is in this direction. Both are equal in magnitude but opposite in the direction. So magnitudes are equal but opposite in the direction. This negative sign is indicating the opposite in the direction. So these are following the Newton's third law, action to pair of action reaction pair. Coulomb's law in vector form, that formula is nothing but the f12 bar equal to 1 by 4 pi epsilon naught q1 q2 by r21 cube into r21. This we found here. Okay, next we are going to write the Coulomb's law in position vector form. Position vector form means, so we are going to write the formula with respect to the origin. Okay, so now this is the q1 charge. Now this is the nothing but the xy coordinate system, and this is the origin. So this is the q1 charge. The position vector of the q1 is r1 bar and position vector of the q2 is r2 bar. That means with respect to the origin, the distance of q1 is r1. From the origin, the q2 distance is the r2. Okay, so now here if you are finding the force on the q1 charge due to the q2, so force on the q1, that means here also we are considering that these two charges are the like charges, so repulsion take place. This is the force on the one due to the second charge. So in this case the vector also r2 1 bar, so distance from 2 to 1, r2 1 bar. Okay, so now here from this triangle law, okay, now this is in this direction, this is in this direction. So we are finding the force from on the one due to 2 now, so in this direction force is acting, so distance also in this direction. So now here if you consider this is a triangle, from the triangular law r2 and r21 bar, these two are in the order but this is in the opposite order. So then this sum of these two equal to the this one. Okay, so we can write it as r21 bar plus r2 equal to the R1 bar. Okay, this is in the opposite and these two are in the same order. This is not in the order, this is opposite. So now R21 plus R2 equal to R1. From this, R21 bar equal to the R1 minus R2, R1 bar minus R2. Okay, I did same thing here. So this is the thing. So now already we found this formula. So F12 bar equal to 1 by 4 pi epsilon Q1 Q2 by R21 cube. R21 cube place I am writing R1 minus R2 whole cube. This we have to consider here magnitude into R21 bar. So place my R1 bar minus R2 bar. So similarly the force on the second particle due to the first one in this direction F21. So F21 equal to same way we have to do, we will get. So general, so first one I am using the I and 2 I am using the J. So in the general form I am writing Fij equal to the 1 by 4 pi Qi Qi into Qj by R21 cube place में what we are writing R1 minus R2 whole cube ना 1 means I, 2 means J, Ra minus Rj cube into R1 minus R2 plus Ra minus R. This is the general formula, remember. Okay, this one, this is the position vector form. This R1 is nothing but the distance of the Q1 from the origin. R2 is nothing but the position of the Q2 from the origin. Okay, you have to remember this position vector form also important. And the next some important points of the Coulomb's law. First, the electrostatic force is central force. That means here we have the one charge plus and here also one more charge plus, and this body, this is the center of this charge and this is the center of this charge. The force act along the line joining the centers of two charges. Okay, now force is act in this direction. Suppose this is positive, this is positive. So on this positive charge due to this one, force is in this direction and this one in this direction. So that means here the force is acting along line joining the centers of the two charges. Next force is electrostatic force is obeying the inverse square law. Already we discussed electrostatic force between the two charges is inversely proportional to the square of distance between them. So that is nothing but it is obeying the square's law. Next, charges are assumed to be rest. So whenever we are applying the Coulomb's law, then assume that charges are in the rest. Next, charges assumed to be point particles. Here we have to consider these charges are point size. Point size means here this is the one charge, this is the one more charge, and compare with the size of the charges, the distance between the charges is more, then these charges are considered the point charges. So now this Coulomb's law applicable to the only point particles only. Next, don't consider sign of the two charges. That means whenever we are finding the magnitude, of the force between the two charges, then no need to consider the sign of the two charges. But if we are writing the Coulomb's law in vector form, then we have to consider the sign. Okay, and next, when two identical bodies having the charges q1 q2 respectively are brought in contact and separated, then the charge on each body is q1 plus q2 by 2. That means here two charges, this is the q1 and this one is the q2. Two charges are there. Now keep these two charges in the contact, then both will be shared and the net charge is q1 plus q2. Okay, net charge on this system is q1 plus q2. Yesterday already we discussed. Now we are separating this one. If we separate these two, then what will happen? This charge will be shared by these two particles, two bodies in equal. So this net charge will be divided equally by these two bodies. That means q1 plus q2 by 2. This is also have the q1 plus q2 by 2. This is the meaning of this. Okay, next see the problems on the Coulomb's law. So first problem is 2 point charges q1 and q2 are 3 meter apart and their combined charge is 20 microcoulombs. So combined charge means q1 plus q2 equal to the 20 microcoulombs and these are 3 meter apart. So that means here these two charges are equal to the 3 meter distance and this one is a q1, this one is a q2. Okay, so then if one first question here, if one repels other with a force of force equal to the 0.075 newtons, calculate the two charge. If one repels other, this two repulsion takes place means these two are either both are positive or either negative. That means like charges. Okay, so then we have to find the what are the two charges. So we know the formula already. The force, electrostatic force between the two charges, F equal to the 1 by 4 pi epsilon naught q1 q2 by r square. F value they given 0.075. 1 by 4 pi epsilon naught value we know already, 9 into 10 power 9, and q1 q2 values is nothing but the capital Q1 and small capital Q2, q1 q2 by r square. Distance between them is the 3 meter. R square means 3 square is 9. Okay, so from this we will get q1 q2 equal to the, okay, this 9 and will get cancelled, and q1 q2 equal to, and after simplification I am going to write directly, that is nothing but the 75 micro coulomb square. This value we will get. Okay, so first, according to the first, the combined charge is nothing but the mu1 plus mu2, q1 plus q2 equal 20 micro coulombs. So now by using the formula we got relationship between the q1 is q1 q2 equal to the 75 micro coulomb square. This is the second equation. We have to solve these two equations. So that means here q1 into q2 plus q2 equal to what we can write, 20 minus q1. Okay, 20 minus q1 equal to the 75. Why? Because here micro coulombs, here also micro coulombs. Now simplify this one, we will get the q1 value is q1 equal to the 15,5 micro coulombs. Okay, if q1 is 15, then q2 equal to 5. If q1 equal to 5, q2 equal to the 15. Like this we will do. That means both are positive, other both are, here we are getting the both are positive values. Okay, now same manner you have to do this B also. Okay, now so and get and post the answer in comment section. Okay, same way do the problem. Next question is, a charge q is divided into the two parts. Here q charge is divided into the two parts. That means it is divided into the q1 and q2. That means sum of these two charges is equal to the capital Q. Okay, so calculate the ratio of the charges on the divided parts such that force between the divided parts is the maximum. Okay, so force between the two charges is maximum. Then what are the charges of the two parts we have to find. Suppose q1 charge equal to the small q I am assuming, then q2 equal to what will we get, q minus q1, capital Q minus q1. q1 is nothing but q. So one part is a small q and other part is the q minus q. So then force of electrostatic force between the two charges, so F equal to the k into small k into r1 by 4 by epsilon naught q1 q2 by r square. q1 value is small q, q2 value is q minus q by distance between them is r square. Okay, so then to get the maximum force we have to differentiate this equation with respect to the charge dq. Then differentiate with respect to the q and equate to the 0. Then we will get the charges. Instead of doing in this method, simply I will tell, just remember one thing, that means if a q charge is divided into the two parts and force between the two charges is maximum, means if two charges are divided equally, then that the force of electrostatic force between the two charges is the maximum. That means this q is dividing into the two equal parts, q by 2 and q by 2. Then the force of electrostatic force between these two charges is the maximum. Then they are asking a ratio. That means here q1 equal to the q by 2 and q2 also equal to the q by 2. They are asking the ratio. So q1 by q2 equal to the q by 2 by q by 2 1. So we will get see the next question, third question. A copper atom consists of copper nucleus that has 29 electrons surrounding it. The atomic weight of copper is 63.5 gram per mole. Now take two pieces of copper, each weighing 10 gram, and transfer an electron from one piece to the other for every 1000 atoms in that piece. Okay, calculate the Coulomb force between the two pieces after the transfer of electrons if the pieces are 1 centimeter apart. Given Avogadro number value given, charge on the electron they given. That means first copper atom ki atomic weight is 63.5 gram. So for 63.5 gram of copper, we have the 6 into 10 power 23 copper atoms. Okay, then they are saying that take the 10 gram of each. Okay, na? So two pieces we have to take, each piece ka mass is 10 gram, copper each weighing the 10 gram. So 63.5 gram copper, we have the 6 into 10 to the power of 23 atoms. Then in 10 gram of copper, how many number of atoms that we have to find? So number of copper atoms equal to 10 by 63.5 into Avogadro number is 6 into 10 power 23. Okay, so number of copper atom in each 10 grams. Okay, so in 10 gram copper, we have the this many number of the copper atoms. Okay, so next here they are saying that we have to take the 10 gram of copper here and 10 gram of other piece copper, 2 10 gram pieces we have to take. Then electron is transferring from the one piece to the other piece. Okay, electron is transferring from the one piece to the other piece, and one more the condition they given, for every 1000 atoms. Okay, for every 1000 atoms. Okay, for the one electron is from transfer from one piece to the other for every 1000 atoms. Okay, so here how many number of atoms in the 10 gram? This many number of atoms there. Okay, so for every 1000 atoms, one electron is transferring. Means how many electrons transferring? So number of electrons transferring equal to the this by 1000. Then we will get. So this is how much? 10 into 6 into 10 power 23 by 63.5 into 1000. Okay, these are the number of copper atoms in the 10 gram copper. Okay, 10 gram piece. Okay, now for every 1000 atoms, it is transferring the one electron from one piece to the other piece. Okay, then for every 1000 atoms it is transferring one electron. So for this many number of atoms, so how many electrons are there, that how many electron transfer that we are finding? So n equal to this much we will get after some this many electron transfer from this piece to the this piece. Now charge on this piece and the charge on this is losing the electrons. How many electrons this is losing? Same amount of electron this is gaining. So what is the charge on each? So Q equal to the N into E. So now Q equal to the N is nothing but this one, 10 into 6 into 10 power 23 by 63.5 into 1000 into E is the charge of electron, 1.6 into 10 power minus 19 coulombs. Okay, after simplification we will get the value is almost 1920 by 127 coulomb. Just to the simplification we will get this one. Okay, so this is losing the electron and this is gaining the electron. So this is getting the positive charge and this one is getting the negative charge. Okay, so both have the same charge, but this one is a positive and the magnitudes are same. Okay, this is the positive and this one is a negative. Now we have to find the force of attraction between this one. Why the attraction? Means this has the positive and this one has a negative. So force of attraction equal to the, we know already, 1 by 4 pi epsilon naught Q1 Q2 by R square. So what is the charge on this one? 1920 by 127 coulombs. What is the charge on this one? Minus 1920 by 127. So Q1 into Q2. So both have the same charge now. Q into the Q square. That means 1920 by 127 whole square by, okay na, 1 by 4 pi epsilon Q1 Q2 by R square na, R square value. Here already they given, these are separated by the something value they given 1 centimeter. Okay, 1 centimeter apart. Okay, R square. So convert the R is nothing but the 1 centimeter na. So 1 centimeter is nothing but 10 power minus 2 meters. Now R square means 10 power minus 2 meter whole square. Okay, 10 power minus 2 whole square. After simplification, we will get this value is 2 into 10 power 16 newtons. 2 into 10 power 16 newtons. Next question, a spherical region of space has a distribution of charge such that the volume charge density varies with the radial distance from the center R as rho equal to rho naught R square and 0 less than or equal to or less than or equal to or, where rho naught is a positive constant, calculate the total charge q on a sphere. This is the question to find out the total charge on the sphere. Okay, now we have the sphere here. To find out the total charge q on this sphere, this sphere ka radius is capital R. To find out this one, we have to consider an infinite small concentric spherical element of thickness dr. Okay, this is the small concentric spherical element of thickness is the thickness of this one is the dr. Okay, now this is the dr and the radius is the r from the center. Okay, so see now here charge distribution we will get later. Here I will tell you. So this sphere is nothing but the three-dimensional one. So from this volume charge density, so volume charge density rho equal to the volume charge density of this small element. I am going to find volume charge density formula. Volume charge density equal to the charge, okay, charge per volume. Okay, so now I am considering the very one infinitely small element. So the charge on this element is very small, dq. Okay, total charge on the sphere is a capital Q. Okay, but we are considering very small element. The small element charge in the small element is dq, and the volume of this one is the dv. Very this small element ka volume also very small, dv. Okay, so the volume equal to the volume of the sphere, dv equal to the small element ka volume equal to the surface area of this one into thickness. Surface area is nothing but radius of this one is a smaller. Surface area of this sphere is 4 pi r square into thickness of this one is how much, dr. So dv equal to 4 pi r square dr. So now from this dq equal to what we can write, dq equal to the rho into dv, and dq equal to the rho value already they given, so it is varying with the distance from the center, that is rho equal to rho naught r square. So rho place में rho naught r square into dv. dv value also we found here, 4 pi r square into dr. So now dq equal to the rho naught r square into rho naught r square is 4 pi r square into r square, r power 4. Okay, so 4 pi r power 4 into dr. Okay, so to get the total charge we have to integrate with the proper limits. So now total charge in the sphere is a q. We have to find that one. Q equal to the integration of the dq equal to the, here the radius is varying from center 0 to the capital R. So 0 to capital R, 4 pi rho naught r power 4 dr. Okay, so from this we can write q equal to the 4 pi rho naught are the constants. Rho naught already given, positive constant. R is a varying here to the here r power 4. So integration from 0 to r power 4 dr. So q equal to the 4 pi rho naught into r power 4 integration. So r power 5 by 5. The limits are, upper limit is capital R, lower limit is 0. So now q equal to the, substitute the upper limit and the lower limit, we will get 4 pi rho naught into r plus में capital R power 5 by 5. If you substitute the 0, then we will get the second term 0. So the answer is 4 by 5 pi rho naught into r power 5. So this is the answer. And the next question is, a wire of length L is placed along the x-axis with one end at the origin. Okay, suppose this is the x-axis, this is the y-axis. Now rod is placed along the x-axis, one end is at the origin. The linear charge density of the wire varies with the distance x from the origin as lambda equal to the lambda naught into x square by L. This value they given, where lambda naught is a positive. Determine the total charge q on the rod. Okay, similar way we have to find, but this is the three-dimensional diagram, and this is the rod. Rod is a one-dimensional one. So one-dimensional we will consider the linear charge density. So linear charge, that means from the origin at x distance. At x distance we have to consider very small element of this rod. That length is nothing but the dx. Okay, so now this small element linear charge density we have to find. So linear charge density equal to the charge per length. So the total charge on this one is a q. For small element, the charge on this one is a very small dq dq by the length of the small element is the dx, dq by dx. Okay, so now from this dq equal to the, we will get lambda into dx. Now dq equal to the lambda value is lambda naught x square by l into dx. Now to get the total charge on this rod, we have to integrate with the proper limits. So now q equal to the integration of dq. So if we integrate this dq, we will get the total charge, and then total charge is equal to the q. So here 0 to total length of this one is the l, the given already length is the l, so l, so 0 to l we have to do. So lambda naught x square by l into dx. So we can write it as this one, lambda naught by l into integration 0 to l x square dx we will get. So now lambda naught l by x square integration is x cube by 3, x cube by 3, the limits are 0 to l. So now total charge on this one is lambda naught by l into, if we substitute upper l cube by 3 we will get l cube by 3, lower limit 0 we will get. So finally we will get lambda naught l cube is in l square by 3. This is the answer. Okay, next see the sixth question. Two identical balls each having density rho are suspended from a common point by two insulating strings of equal length. Both the balls have equal mass and charge. In equilibrium, each string makes an angle theta with the vertical. Now both the balls are immersed in a liquid. As a result of immersion in the liquid, the angle theta does not change. The density of the liquid is sigma. Find the dielectric constant of the liquid. Dielectric constant of the liquid we have to find. So see here, two identical balls I'm considering. This is the one ball and this is the one more ball. Two balls are suspended from a common point by two insulating strings, and these are making some angle theta also they given. So this is the support rigid surface. From here these two are suspended, with respect to the vertical. These are making the same angle, this is making the theta. What they mention, in equilibrium each string makes an angle theta with the vertical. This is making theta, this is also making the theta. Now these are in the equilibrium. If these are in the equilibrium, next they mention identical charges, both have the same charge. Okay, equal mass and same charge. Okay, so then this both have the same charge means repulsion takes place. Okay, this is the q and this one also q, both have the same charge. This will repel in this direction and this will repel this one in this direction. Okay, so in this case how to solve the problem means, so the electrostatic force on this sphere is in this direction. This is the electrostatic force, and the weight of this one is acting in this direction, downward direction. This is the mg. Okay, na weight, okay, weight equal to the mg. Now extend this one. Okay, this one with the vertical, this is making the theta angle. So here also this will make the angle theta. Okay, now this is the q channel, this is the angle the theta. Okay, so this side force is Fe na, so extend this one, this is also nothing but the Fe. So easily we can get, this is the theta. From this tan theta equal to the, tan theta equal opposite side is nothing but the electrostatic force Fe by adjacent side, this is nothing but the weight mg. Okay, mg. This is the first case. Next what they are doing, they are keeping this balls are immersed in a liquid. As a result of immersion in the liquid, the angle theta does not change. This is not changing, the distance between these two is not changing. That means now they are keeping in the water, liquid. Okay, this is the one ball, this is the one more ball. So in this case also with the vertical making the same angle. So if we immersed in the water, okay, if immersed in the water, charges are q and q only. This is repelling in this direction, force of electrostatic force, and weight is acting in this direction only. But here what will happen, if we keep it in the water, okay, if we keep it in the water, this setup, then weight is acting downward direction. This water will exert the force on the upward direction. Okay, this is the weight and this is the force due to the water. That force is nothing but the buoyancy force. Okay, so in this direction electrostatic force, and here in the downward direction weight is acting. Whenever we are immersing in the liquid, then liquid is exerting force on this one is the upward direction Fe, and then this extend this one, this angle is same dimension theta, so this side force is nothing but the Fe only, Fe dash I am assuming here, Fe here Fe dash. Okay, from this tan theta equal to the tan theta opposite side Fe dash by here this one we have to find. So net weight we have to find. Okay, the resultant weight. So weight is in the downward direction and the buoyancy force is acting in the upward direction. So net weight equal to the this weight minus buoyancy force. Weight is nothing but the mg minus buoyancy force is Fb. Okay, so now this here, whenever this is in the air, so electrostatic force is a Fe. Now if we are immersed in the liquid any medium, and next they are saying that the angle here the theta, here also angle is a theta, same charges keeping the same distance, then electrostatic force between the charges will be decreases. How much it will be decrease means it will be decreases by the K factor of K. Already we discussed that one. This is the K is the dielectric constant. They are asking find the dielectric constant of the liquid. This K only we have to find. Okay, so from here tan theta equal to Fe by mg we got, and here tan theta equal to F dash by mg minus mg. This is the first equation. This is the second equation. So from 1 and 2 tan theta equal to tan theta. So Fe by mg equal to the, so here Fe dash by mg minus Fb. Fb is nothing but the force due to the liquid in upward direction. So now Fe by mg equal to the Fe dash by mg minus buoyancy force. Buoyancy force का formula I am writing density of the liquid. How much the given density of the liquid? The density of the liquid is sigma given rho, and the volume of the body in the liquid. So volume, total immersiveness, total volume we have to consider into G. Okay, so density of the liquid into and the volume in the liquid. So total immersiveness, total volume into G. This is the formula. So now this is nothing but the sigma V G. Okay, so I am writing here M E by M into G. M into G, mass is nothing but the mass density equal to the, we will write density of the spheres also the given, density is the rho. So density equal to the mass of the sphere by the volume of the sphere. From this mass equal to the density into volume. So here we can write rho V, mass placement rho V into G equal to the Fe dash equal to already we know. So Fe by K into, we are getting here M plus what will we get? Rho Vg minus sigma Vg. Okay, na? So now weight is whenever we are finding the weight we have to consider the density of the body and the volume of the body. Whenever we are finding the buoyancy force we have to consider the density of the liquid and the volume of the body within the liquid. Okay, remember that point. Now Fe will be cancelled out, then we will get 1 by rho Vg equal to the 1 by K into here rho Vg minus sigma, Vg common. So if I take the Vg as a common, rho minus sigma. So this Vg will be cancelled. K send this side. K equal to rho will come this side. Rho by rho minus sigma. So this is the dielectric constant they are asking the K value. See the seventh question. A charge Q equal to 1 microcoulomb is placed at a point P 1, 2, minus 4 meters. Find the electric force on a minus 17 microcoulomb charge at a point Q 4, 6, minus 16 meter to the nearest approximation. So this one is the first charge I am considering. This one is the second charge. So that means Q1 equal to the 1 microcoulomb and Q2 equal to the minus 17 microcoulombs. And Q1 location they given. So P equal to the given. I am assuming it as R1. R1 equal to the 1, 2, minus 4 they given. I am writing in terms of the unit vectors. This is the x coordinate y and z. X may along the x direction unit vector is I cap, along the y unit vector is j cap, and along the z direction unit vector is k cap. I am writing it. So now 1 means I cap plus 2 j cap minus 4 k cap. Next R2 equal to the position of the second charge minus 17 microcoulomb position they given 4 6 minus 16, so 4 I cap plus 16 j cap, sorry, plus 6 j cap minus 16 k cap. This is the given. They are asking force on the minus 17 microcoulomb. Minus 17 is not cute. Force on 2 due to the 1. That means here Q1, this is the Q2. These two are there. Okay. And force on the Q2. So here with respect to the origin we have to find. So see now this is the system. Okay, this is from the R1 distance from the origin, and this is the R2 distance from the origin position, and this is the X and Y. This is the diagram. Now we have to find the force on the Q2 due to the Q1. So Q1 is the positive charge, Q2 is the negative charge. Force on this one due to this one now is the attractive in nature. Force on 2 due to the 1, okay, in this direction, attractive. So now F21 equal to the, so in the vector form I am writing. So F21 are equal to, already I given the formula, F21 equal to the 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R2 minus R1 whole cube into R2 bar minus R1 bar positions. Okay, so from here we have to find the R2 minus R1 first. So R2 minus R1 equal to, R2 is the 4i minus R1 is I, 4i minus I, 3i cap, 6j minus 2 plus 4j cap, minus 16 minus of minus plus 4 minus 12k cap. Okay, this is the R2 bar minus R1 bar value. Okay, now we have to find the magnitude of this one. Magnitude also we need. So magnitude of R2 minus R1 is nothing but square root of x square means 9, y square means 4 square 16, plus 12 square means 144. Then we will get this value, how much is 16 plus 9, 25, 169 means 13 we will get. Okay, now substitute in the formula, we will get the answer. F21 bar equal to the 1 by 4 pi epsilon naught, 9 into 10 power 9 into Q1 value is 1 microcoulomb means 10 power minus 6 into Q2 value is minus 17 microcoulombs, minus 17 into 10 power minus 6. Vector form I am writing, so minus by R2 minus R1 whole cube. R2 minus R1 is almost 13 whole power 3 to R2 bar minus R1 bar. R2 bar minus R1 bar value is 3 I cap plus 4 j cap minus 12 k cap. Okay, na? So simplify it, we will get the answer. This simplification is homework to you. See the 8th question. Two identical oppositely charged metallic spheres placed 0.5 meter apart attract each other with a force of 0.108 Newton. When connected to each other by a copper wire for a short while, they begin to repel each other with a force of 0.036 Newton. Find the initial charge on the each one of them. Okay, initial charge on the metal spheres we have to find. See now, initially this is the Q1, Q2. These two are separated by the 0.5 meter, and force of attraction between this is 0.108 Newton. Force, the attraction force is there, means both have the unlike charges. If this is the positive and this one is the negative, if this is positive, this one is the negative, unlike charges we have. So from the electrostatic force formula, F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. I am finding the magnitude only, so no need to consider the sign of the charges here. So attractive force they given 0.108 into 1 by 4 pi epsilon naught 10 into 10 power 9 Q1 Q2 by R is nothing but 0.5 whole square. After simplification we will get Q1 Q2 equal to 3 into 10 power minus 12 Coulomb square. This value we will get first. This is the equation number 1. And the second, what they are doing, they are keeping the two charges at the same distance only. They are not disturbing this one. They are connecting these two charges by the copper wire. If you connect the copper wire, the charge will be transferred from one sphere to the other sphere. First, initially it has the suppose positive. If we can press Q1, this one is a minus Q2. So the charge is Q1 minus Q2. Both will divide, share that one equal. So Q1 minus Q2 by 2, and this one also have the charge Q1 minus Q2 by 2. That means both will get the similar charge, and that is equal to the Q1 minus Q2 by 2. Okay, the final charge on this one is Q1 minus Q2 by 2. Final charge on this one is Q1 minus Q2 by 2. And both will get the same charge due to this like charges. Due to this one, repulsion takes place. How much repulsion takes place means 0.036 newtons they given, 0.036, and distance between these two is same, 0.5 meters only. From the formula, F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. F value they given 0.036, and 1 by 4 pi epsilon naught value is 9 into 10 power 9. And Q1 Q2 both have the same charge, that is Q1 minus Q2 by 2. So Q1 into Q2 means this Q into Q whole square. So Q1 minus Q2 by 2 whole square by R square. R value is 0.5 whole square. Okay, here Q1 Q2 both have the same value, that's why I am writing the square here. So after simplification, this one Q1 minus Q2 equal to, we will get 2 into 10 power minus 6 coulombs. So this is the first equation, this is the second equation. Okay, solve these two equations, we will get Q1 charge is this much and Q2 charge is this much. So the simplification, simplifying these two equations is the homework. Whether we are getting same or not, check it once. So Q1 value is 3 microcoulombs, Q2 value is minus 1 microcoulombs. Why means initial charges they are asking. Initially attraction in between these two charges means both have the both are unlike charges. So Q1 is positive and Q2 is negative. Q1 value is 3 microcoulombs and Q2 value is minus 1 microcoulombs we are getting. Okay, see the ninth question. Two identical beads each have mass m and charge q. Okay, these are the two identical beads. Mass is m, charge is a q. Each have the same mass and same charge. When placed in a hemispherical ball of radius r, this is a hemispherical ball, radius of this one is a capital R, with frictionless non-conducting walls, the beads move and at equilibrium they are a distance r apart. When these two are in the equilibrium, then distance between these two is nothing but the capital R only. So determine the charge on each bead. What is the charge on the each bead they are asking, that we have to find. So see now, whenever these two are equilibrium, then the forces acting on this one we have to find. Easy way I will tell you, just see now, first bead I am considering. Okay, this is the bead, both have the same charge now. So this is exerting the force on this one, so repulsion takes place. Why? Because both have the same charge. So due to this charge, force acting on this one is in this direction. So now force acting on this is in this direction, F. Okay, and weight of the bead, weight of the bead is vertically downward direction, weight of the bead is vertically downward direction, m into g. Okay, now see here, this is the radius of this hemispherical ball r. Now distance between these two beads when these are in equilibrium also capital R. Here this is the capital R, here this is the capital R, this is also capital. That means this is the equilateral triangle, and now this angle is nothing but the, each angle is 60. This is also 60 degrees. Now if you extend this one in this direction, so this I am extending in this direction. Okay, now so now angle between these two is 60 degree, then this one also 60 degree. That means here also this is the 60 degrees. Okay, so from this one, so this is the angle 60 degrees now. So mg, this is mg means in this direction also this is nothing but the mg only. From this we will get very easily. So here tan theta equal to the opposite side, this is the mg, opposite side, by adjacent side is the f, adjacent side is the f. So now theta equal to how much is 60. So tan 60 degrees equal to the mg by f. F is the electrostatic force between these two charges. So electrostatic force between these two charges is nothing but the F equal to the 1 by 4 pi epsilon naught q1 q2. Both have the same charge, q into q square by distance between them, square of distance between them, r square. So now I am writing F place में this one, 1 by 4 pi epsilon naught q square by r square. Okay, so from this they are asking the determine the charge on each bead. Q value we need, this Q we have to find. So then tan 60 value is root 3 equal to the mg by q square into this 4 pi epsilon naught square will go upside, 4 pi epsilon naught r square. Now q square send this side, so q square equal to the mg 4 pi epsilon naught r square by root 3. Okay, so from this we can find q equal to the mg 4 pi epsilon naught r square by root 3. So send the square to this side, it will become square root, that means power is 1 by 2. So this is the charge on each bead. In this way we have to solve the problem. Okay, see the next 10th question. Two particles each of charge. So two particles q1 equal to 10 power minus 7 coulombs and q2 also equal to 10 power minus 7 coulombs, and mass is the 5 gram. Both have the masses, m1 equal to 5 gram they given, this is also m2 equal to 5 gram only. Both stay in limiting equilibrium on a horizontal surface, on this horizontal surface, limiting equilibrium. The particles have a separation of 10 centimeters. So r equal to the 10 centimeter. So r equal to the 10 into 1 centimeter equal to 10 power minus 2 meters. Then r equal to 10 power minus 1 meters. This is nothing but the 0.1 meter. Okay, assume the coefficient of friction between each particle and the table to the mu. Okay, so here this is the particle q1. Okay, this is the particle q2 is in. So between this these two are arranged on the table. So the frictional coefficient they given here, the frictional coefficient here, the frictional coefficient is given, that is equal to the how much. Assume the coefficient of friction between the each particle and the table to be mu only. Calculate mu value only we have to calculate. Okay, see now whenever this are in the limiting equilibrium, this point you have to remember. So both have the same charge now. So this will be repel in this direction, this will also repel this one in this direction. Okay, so force on the q1 due to the force on the q2 due to the 1. Okay, repulsion. So in the limiting equilibrium means this force is exactly equal to the frictional force. It is frictional force. If this force is more than this, then it will go in this direction. Now it is in the limiting equilibrium means the force of repulsion between these two is equal to the frictional force. Now I am taking this one, I am considering this one, and repulsion force between this one is nothing but the F12 is in this direction, and frictional force is in this case F. So it is the frictional force, and limiting equilibrium means the repulsion force is equal to the frictional force. Okay, repulsion force, the electrostatic force equal to the formula is 1 by 4 pi epsilon naught q1 q2, both have the same na, q1 into q2 q square, then 10 power minus 7 whole square by r square, r value is 0.1 whole square equal to the frictional force formula, F equal to mu into m into g. This is the formula. So now mu into m value they given 5 gram. 5 gram is 5 into 10 power minus 3 to g value is 10. Okay, now simplify it. After simplification you will get the frictional coefficient value is the mu equal to the how much you will get means 0.18 you will